Hello, my dear students. Today we are going to start a new module of electric drives, that is selection of motor power rating. Now, how will you choose a particular motor in an industry? So, power rating of a motor and its selectivity is very important, and that's what we are going to study. That what are the guiding factors of selection of a motor in an industry? So, actually, let us study the heating and cooling curves of a motor when it is operated. So suppose there is a motor which is turned on at t equal to 0 that is over here, and it is allowed to operate it for t equal to say t1 time, and after that it is turned off. So what will happen? Electric power will flow through the conductors of the motor, and there will be I square R loss in the conductor. And what happens due to this I square R loss? There will be heating in the motor, and that will be transmitted to all the motor parts. So as a result, the temperature, which is denoted by theta, it is in degrees Celsius in the y-axis, that will rise. So it is rising like this, and at when t equal to t1, when it is turned off, so the current through the conductors of the motor, that falls to 0, and eventually what happens? The motor cools down. This is known as the cooling curve. So there is motor heating, and secondly there is motor cooling. So now, there is a thermal model of motor cooling. So the motor cooling is characteristics by a separate cooling time constant, which is known as CTC, for running and stop motor states. The typical ratio of stop to running CTC is 2:1. So if we zoom into this part, so you will see that there are some parameters. Hot to cold ratio, motor stopped after the overload trip, cool time constant 30 minutes. So these are the parameters, and what thermal capacity has been used, that is given over here. So this is the time in minutes, and this is the thermal capacity used. So it takes the motor typically 5 time constants to cool. So let us study the thermal modeling of a motor for heating and cooling. So an electrical motor and drive operates. There is a generation of heat inside the motor. The amount of heat generated inside the motor should be known as accurately as possible. So you should know that what amount of heat is generated inside the motor, and if you know that, only then thermal modeling of the motor is possible, and thermal modeling of the motor is necessary also. So the material of the motors and the shapes and size of the motors are not unique, they are same. So the materials vary from motor to motor, and the shapes and size of the motors also vary. from one another, but the generation of the heat does not alter very much depending on the characteristics. So it may happen that the motors, they are of different shapes, they are of different size, but the generation of the heat does not alter very much depending upon the characteristics of the motor. So a simple thermal model of any motor can be obtained assuming it to be a homogeneous body. What is meant by homogeneous body? A homogeneous body means all the parts have uniform constituency. So that is meant by the term homogeneous, that each and every portion of the body has uniform constituency. So the main aim of this modeling is to choose the appropriate rating of the motor so that the electric motor does not exceed its safe limit during the operation. So this is one assumption, that all the body parts have uniform constituency. So now there are some parameters which needs to be first noted, and before analyzing the entire thermal model. So at time t, let the motor have the following parameters. Let us say that small p1 is the heat developed in joule per second or watt. P2 is the heat dissipated to the cooling medium in watts. W is the weight of the active parts of the machine. So these are the active weight of the active parts of the machine. So all these notations are used to develop the modeling of the machine during heating and cooling. So all these parameters are noted after operation of a time t. So there are few more parameters. Small h is the specific heat in joules per kg per degree centigrade. A is the cooling surface in meter square. Small d is the coefficient of heat transfer in joules per second per meter square per degree centigrade. Theta, it is the mean temperature rise in centigrade. Now if time dt, let the temperature rise of the machine be d theta. Suppose initially the machine was operating at a temperature of theta 1, and now after time t it is operating at a temperature of say theta 2. So theta 2 minus of theta 1, that is equal to d theta. So therefore, by law of conservation of energy, heat absorbed in the machine is equal to heat generated inside the machine minus heat dissipated to the surrounding cooling medium. So d theta, that is equal to P1 dt minus P2 dt. Now what is P2? P2 is equal to theta into d into a. Now substituting the value, we get C d theta dt is equal to P1 minus d theta. So again this is a first order differential equation. So C is called the thermal capacity of the machine in watts per degree centigrade. Capital D is the heat dissipation constant in watts per degree centigrade. So when we acquire the first order differential equation, which is this one, from here if we solve that, it is theta is equal to theta ss plus k e to the power minus t by tau, where theta ss is equal to p1 by capital D and capital T is equal to c by d. So these are the notations. This is the solution of a first order ODE. So that means if we analyze this, we get two parts. One is theta ss and the another part is k e to the power minus t by tau. What is theta ss? Theta ss is the steady state temperature. That means it is the steady state temperature after all these exchanges. And you see, this is the transient rise in temperature, which is k e to the power minus t by tau. So what will happen at t tends to infinity, that means sufficient long time. So what will happen? This part will tend to 0. That means at one point of time you will get theta equal to theta ss when t tends to infinity. Now from here, if we put t equal to 0, if we put the value of t equal to 0, then we get k is equal to theta by theta ss. Now if you substitute this, you will get this particular value. So theta is equal to theta ss into 1 minus k e to the power minus t by tau plus theta 1 e to the power minus t by tau. So this is the solution of this equation. So from the above equation, we can find out the rise in temperature inside a working machine, which is very near to being the accurate. And if we plot a graph for the variation of the temperature risk with time during heating and cooling, thus the thermal modeling of the motor gets complicated. Now our objective is, what is our objective? Our objective is that after some point of time, we want to see that what is the heat generated by the machine, because this heat will help us to determine that what insulation we will use in the conductors. That is the determining factor. What materials we should use in the machine. This is the guiding factor. For that you need to know the thermal modeling of the machine. As because you know when current flows through the conductors, I square R loss is there, which is generated in form of heat. And what will happen, all the insulation layers of the conductor that will be highly stressed, and at one point of time, if the temperature rise beyond a particular value, what will happen? The insulation layers will be overstressed, and at one point of time the insulation will fail. So there is every risk that there is an insulation failure resulting in a severe short circuit in the machine. Now, thermal model of a motor for heating and cooling. So electric motors are used and to control the thermoelectrical devices that are employed. But the operating time for all motors are not the same. Why? Because you see, it is dependent on what purpose you are using the motor. Why you are using the motor? What is its purpose? That is dependent on the industry. It may be a cement mill, it may be a paper mill, it may be a hoist drive you are operating. There may be different industries, and the motors are of different duties. So some of the motors runs all the time, and some of the motors run time is shorter than the rest period. So depending upon this, the concept of motor duty class is introduced. On the basis of this duty, cycles of the motor can be divided into 8 categories. So what is a motor duty? That means it is the ratio of T on by T. This we have learnt in power electronics. It is the alpha, that is the motor duty, it is on the on time of the motor divided by the total time period of the motor. So there are 8 classes: continuous duty, short time duty, intermittent periodic duty, intermittent periodic duty with starting, intermittent periodic duty with starting and breaking, continuous duty with intermittent period of breaking loading, continuous duty with starting and breaking, continuous duty with periodic speed changes, and the last one is continuous duty. So these are the different type of duty parameters of a motor. These are all the possible combinations. Now what is a continuous duty motor? This duty denotes that the motor is running long enough, there will be an H over here, and the electric motor temperature reaches the steady state value. That is known as continuous duty. So these motors, this is very important, these motors are used in paper mill drives, compressors and conveyors. So these are the applications. So you see, what is the torque profile? The load torque is constant, and that's why it is of continuous duty. So you see the temperature rises like this. The temperature rise, it reaches maximum steady state and it remains constant. So the next part is short time motor duty. So in these motors, the time of operation is very low and the heating time is much lower than the cooling time. So the motor cooks off to ambient temperature before operating again. That's a very very short time duty. So these type of motors are used in crane drives, drives for household appliances, valve drives. These are the applications. That means the motor is getting enough cooling time before starting again. This is known as short time duty. So this is the waveform of short time duty. So here you see the load torque is for a particular period, and the next load torque appears after a very long time. So the motor gets heated to a temperature and it gets enough time to cool down. So perhaps the next heating will be somewhere here. So that means you see it gets enough cooling time. That means the cooling time is, or the idle time of the motor is almost this, very long idle time. So let us stop over here up to this. In the next lecture we will continue with the other classes of motor duty. Thank you.